Metrology. We have with us Professor Vinay Kumar. He's from Jubail Industrial College, Saudi Arabia. He's an assistant professor and researcher with 23 plus years of experience in physics courses, teaching experience, and R&D. Sir, we are thankful to you. You have accepted our request and deliver a talk on a very interesting and important topic related with pressure and its metrology, because this is very important, whether it starts from the pressure in a tire or pressure of atmosphere or pressure of human body. It is all are very important. Thank you very much, sir. I would like to request you to kindly switch on your video so that we can understand, we can see how you are speaking, and we can actually understand what you are saying. We have with us our Honorable Shri B.N. Dikshit, Honorable Director, sir, Director Legal Metrology, Government of India. I would like to request him to kindly speak 2 words so that we can start this workshop. Sir, Dikshit, sir, please.
Thank you, Ashutosh, Director in Charge Legal Metrology, Government of India, and Mr. Jubair from Saudi Arabia. No? So it is great pleasure that he has taken his time to give the lecture on this very pressure and on this type of things. Legal metrology plays the very important role on the pressure measurement, and there is the sphygmomanometers and other type of things that is related with blood pressure measurement in the legal metrology. Apart from that, so a lot of industries are coming to the RRSS for the verification and calibration of their pressure gauges, which is used in the industry for the quality control purpose and the manufacturing purpose. So with these very small words, I pray for the success of the seminars. I hope that Dr. Vinay Kumar, Professor Jubair, and whoever the other scientists are there, they will make this very program very successful. Thank you all. Thank you for hearing.
Thank you. Thank you very much, sir. Now, I would like to request our honorable expert, Professor Vinay Kumar, to kindly enlighten us with his knowledge, experience, and whatsoever he has actually earned with his own experiences. This will be a very good exercise for all of us to listen in. Please, sir, kindly. Over to you, sir.
Thank you, Ashutosh sir and Director sir, for giving me opportunity to speak on this pressure metrology. And my sound is clear and the screen is visual.
Yes, everything is clear.
Okay. So, myself, Dr. Vinay, working here in the physics department of Jubail Industrial College. And my research work is starting in 97, and I work on pressure. I develop many sensors. So today I want to brief you about pressure metrology, how pressure and its measurement can be done. In my presentation of seminar includes introduction, history, pressure measuring devices, pressure sensing, captive pressure sensors, calibration, relaxer ferroelectric material, optimization of pressure sensor, result and discussion and conclusion. Actually, my field is development of pressure sensor using capstar relaxer material. So I will brief you how we can optimize, how we can develop a pressure sensor. But in the starting, I will give some brief about the pressure measuring. In various industry, this pressure is very important. Almost all the industry in our daily life, we need the pressure measurement. And this is accurate pressure measurement is not only required, but it is for safety purpose also. For example, if in our cars, tire pressure is more than the limit, then what will happen? Tire will burst and it will cause fatal accident, serious accident. So the measuring of pressure with accuracy is very, very important. And that pressure gauge must be reliable, accurate, and easy to read. Reliable means we can rely on their data, that this data is correct or not, what it is showing, and it is accurate or not accurate. What is the accuracy of that data, that pressure measurement, and easy to read. Immediately we can read that data, pressure, what we want, in which unit we want, we can read. So all the industry like automated chemical process, refineries, petrochemical process, hydraulic, pneumatic. Here I mention only some industry, energy industry, exploration, everywhere in all the industry we need the pressure measurement. The history of this pressure started since 16th century. In 16th century, the Italian Galileo Galilei was granted the patent. In 16th century, he got the patent for water pump system. In irrigation, generally the canal and lake is at lower level and the fields are at upper level. So we have to pump the water from lower level to upper level. We have to send that, and this can be done by applying the pressure. So Galilei, he developed a water pump system in 16th century and he got the patent also. In 1643, the Torricelli invented the barometer to measure the atmospheric pressure. It is very important to measure the pressure because everything, pressure is force over area. And force is, we have atmosphere above the surface. So there is the mass of the atmosphere multiplied by gravity mg, it exerted force on the object which is on Earth's surface. And that force divided by area is pressure. And you will not believe there is a pressure of force of nearly 1 elephant on our head. So this measuring the pressure is very, very important, atmospheric pressure, and he invented, Torricelli invented barometer to measure the atmospheric pressure. In 1648, Pascal used barometer to show that the air pressure was smaller at the top of mountain. So he measured the pressure above the mountain and Earth's surface, and he shows that pressure is smaller. That's why when we move on the mountains, our blood vessels, which is very thin and near to the skin, is burst. So we have to wear a special suit because this atmospheric pressure is balancing our blood vessels pressure, and when if the outside pressure is less, the blood vessel will burst. In 1650, Jared developed the first efficient air pump. In the 16th century, Galilei invented water pump. He invented air pump. Air can be pumped, air pressure can be generated. In 1849, Borden was granted a Borden tube patent. He invented Borden tube, and this tube is still in used in many pressure measurement devices, Borden tube gauge. In 1803, Agarwal used the deadweight piston on pressure measurement, and this changed the pressure accuracy to a very lower level after inventing deadweight piston gas. And the range of pressure measurement also increased from vacuum to very high pressure we can measure with the help of the deadweight piston gauge. In past few decades, with the advent of digital technology, variety of equipment spread through the market and its application. So many instruments nowadays invented to measure the accurate and reliable pressure in broad range of pressure measurement. Then in terms of legal metrology, or how we can say that this instrument is reliable or it is accurate, or which the observation is showing it is correct one. So we have to test, we have to calibrate that instrument, any instrument, not only pressure, any instrument with the standards. So there are two types of standard. One is primary standard, another is secondary standard. Primary standards measure the quantity or pressure, I am talking about pressure, in terms of physical fundamental quantity, or not need to calibrate other standard. So primary standard is complete and they not need to calibrate against the another. But inter-comparison is there between two standard. We can compare two primary standard of different country or different labs. So inter-comparison will be there to check their accuracy, but they no need to calibrate against the another standard. But secondary standard is need to calibrate against the primary standard, and these are the used to transfer the observation, to transfer the data from primary to the secondary, and to serve the this purpose of the calibration to the floor level, to the ground level. The uncertainty is greater, primary standard is greater than the secondary standard. So here I mentioned some pressure measuring devices. These are some pressure measuring devices. There are three categories of pressure measuring device. One is manometer, another is mechanical gauge, and third one is electronic pressure gauge. In manometers, there are some variety like simple manometer, piezometer, U-tube manometer, single column manometer, inclined manometer. Then differential manometer, two piezometer manometer, U-tube differential manometer, and inverted differential manometer. These manometers are used generally for low pressure calibration, low pressure measurement. Then mechanical gauges, they used elastic property of material, and these gauges are McLeod gauges, Borden tube gauges, diaphragm gauges, Wallow gauge, deadweight gauge, and deadweight pneumatic gauge. Third type of electronic pressure gauges. These pressure gauges are used to automated devices, because we get the signal pressure in terms of electrical signal, and that can easily convert to automated system. And these gauges are MEMS pressure gauge, Prani gauge, ionization gauge, magnetic pressure gauge, thermocouple gauge, and rotor gauge, spin rotor gauge. So here I mentioned some devices, some important devices, and I will explain few of them to understand the concept of pressure measurement. So first is manometer. Very simple instrument. It has a U-shaped glass tube containing a reference fluid. Reference fluid can be mercury or water. And mercury is used in the most of the manometer because it do not stick to the walls of the glass. One end of this U-tube is connected to unknown pressure, and another end can be closed or can be open, depending upon what we are measuring, or we are measuring absolute pressure or gauge pressure. Unknown pressure when applied to this U-tube initially this reference fluid, the reference height of both limbs is same. When we applied the pressure from left side, what happened? This pressure pushes the fluid in the another direction. So there is a height difference between the reference fluid of two limbs. And this height difference can be used by measuring this height difference. We can measure the unknown pressure using the equation delta P gauge pressure equals to P minus P naught equals to rho GH. P naught is atmospheric pressure. So by knowing the density of the fluid, acceleration due to gravity at that point, and height, the difference of two limbs position of reference fluid, we can measure the pressure, unknown pressure. When the terms of accuracy it comes, we have to know the density of liquid, accuracy of density, and the acceleration due to gravity at that point, and also the accurately we have to measure the height between two mercury column. Another popular gauge is Bourdon gauge. Bourdon gauge, we use a Bourdon tube. In the third figure, you can see this blue color tube is the original state tube. So inside this gauge, there is a tube. One end of this tube is connected to unknown pressure, and another end of this tube is connected to the mechanical linkage. And this mechanical linkage is connected to the needle, and when we apply the pressure, the tube got deflected, it increased, its length is increased, and that increment of the length deformed state is transferred to the needle with the help of the mechanical linkage. And this Bourdon tube you saw to measure the tire pressure. We see this type of the gauge. This is Bourdon tube gauge, and copper tube, it is transferring the pressure using elastic property of the copper to the linkage, mechanical linkage, and then convert it to the direct pressure reading. In that electronic gauge, strain gauge is mostly used and most popular. In this case, we use the concept of Wheatstone bridge. And in Wheatstone bridge, as you are aware of, there are four resistance R1, R2, and R3, R4 arranged in the Rx here I mentioned, arranged in the form of a bridge. At the two end, the excitation voltage of this bridge is applied, and other two end, a voltmeter is connected. When this all resistance are balanced, if R1 over R2 equals to R3 over R4, then there will be no voltage between the B and D terminal. So this condition is known as balance bridge. Suppose in balance condition, there one resistance got changed, Rx. For example, say Rx got changed, then what will happen? This bridge will be unbalanced, and there will be some voltage along between B and D terminal. So what will happen? This deformation or this change of resistance, if due to the pressure, then we can measure the pressure indirectly in terms of voltage after applying the pressure on Rx or any one resistor. So when we apply the pressure on resistance, the construction or structure of resistance is shown in second figure. It is in the form of the lengthy copper wire, and it is stick on the surface, and when we apply the pressure on that resistance, it deforms and its length or area got changed, or by changing the length and area, the resistance got changed. When resistance got changed after applying the pressure, we will get some voltage. And after calibrating it or converting it to directly in the display, so digital display can be done. So applying the pressure on any one resistance or strain gauge, this pressure can be read directly by the help of the electronic meter or indirectly in term of voltage. And this voltage can be used to automated purchase. We can use this voltage to make automatic device, switches, actuators. We can use this voltage. Another type of gauge is quartz gauge. Quartz gauge, we use the quartz crystal. The property of quartz crystal is when we apply the pressure on this crystal, it generates the voltage. Reverse of this we use in the our watches, electronic watches, wrist watches, where the voltage apply on the quartz and it vibrates with that voltage. And that vibration is used to calculate the time, and we use this in the watches. Here, directly we apply the pressure on the any quartz crystal, it generates the voltage. And after calibrating, that voltage can be used for measuring the pressure. In piezoresistive gauges, we use same like change of resistivity, electrical resistivity of semiconductor or metal to measure the pressure. So when we apply the pressure, the electrical resistivity of a metal portion or semiconductor got changed, and that change is measured in terms of the voltage, and the piezoresistive gauge works on that principle. And here we can measure accurately for a small differential pressure. Like for example, we want to measure the pressure of outside the room and difference outside the room and inside the room. We can use this piezoresistive gauge. To measure the differential pressure, we can use piezoresistive gauge. And the most commonly and accurate device is dead weight tester. This works upon, this is used as a primary standard also, and it is very simple, cost-effective solution of covering wide range of pressure measurement. In this dead weight tester, the main hard part is the here piston and cylinder assembly. There is a piston and a cylinder, and on the cylinder cover we put masses, and hydraulic pressure for high range and the pneumatic pressure air can be used for the low range. So when we applied the masses on the piston and generate the pressure with the help of this pump, this balance the masses, and these masses floats on the fluid, and masses exert force mg, and by knowing the area of piston we can calculate the pressure by mg over a. This is simple reaction, but for accurate measurement there is a complex equation to measure the, we have to need the accurate measure of the density of fluid, air, many components are there for accuracy. But the basic principle is mg over a, force over area. So here in this construction there is a pump and the storage, oil tank, and piston and cylinder assembly. And measuring device we can put on the right side here. We can connect the any calibrating and measuring device, and we can measure the pressure. We can compare that pressure of that device using the balancing the pressure between two the dead weight and the this on the measuring device. This based upon the Pascal principle. And this dead weight tester is used to cover the wide range of the pressure. For measuring, for constructing the pressure sensor or the electronic gauges, what we need? We need a sensing element which can sense the pressure. Then this displacement or change in the sensing element will then go to the transduction element. Transducer will convert this displacement in form of the electrical signal. Then electrical signal can be modified and conditioned to measure the pressure. So this mechanical element, sensing element can be the plates, cells, tubes, or capacitance, anything we can use to sense the pressure. Then resistance, capacitance also. This is basic mechanism converting pressure into physical movement, and then this movement transduced to obtain electrical signal, and finally we can use, depending upon the application, this type of sensor we can use, and we can convert pressure into electrical signal. So here one type of signal I will pressure sensor I will discuss here, that is capacitor pressure sensor. I developed this pressure sensor, many pressure sensor I developed. Even I got the patent in United States, Europe, India, many country I got the patent also. So capacitor pressure sensor use the thin diaphragm one plate of a capacitor. In capacitor, we know that there is two plates. One plate is in the form of the thin diaphragm. Applied pressure causes the diaphragm to deflect. So diaphragm is deflect, then the capacitance will got change, because capacitance is epsilon naught A over D. It depends upon the area of plates and the distance between the plates. So if the distance between the plates got changed, then capacitance will change. So applying the pressure on the one plate, what will happen? The distance between two plates will got change. Then this change the capacitance, and pressure can be measured in term of the capacitance change. This change can be linear or order of linear, or it can be the quadratic, but the capacitance change is very small, between 50 to 100 picofarad, or sometimes in term of 1000 picofarad also. The change of capacitance can be used to control the frequency of oscillator in the network. So we can, if we want to send any signal, and this change with the help of the pressure, if we want to turn on any device, we can use this concept by changing the capacitance, applying the pressure, capacitance will change, and that can be utilized. And that can be utilized to measure the pressure also. So every instrument I discussed here, the sensors, it need to be calibrated. To mark the calibrate, how we can do? We have to calibrate it very high, like dead weight tester, high accuracy instrument. So here the structure left side, you can see dead weight tester is there. Blue color, this is the hydraulic fluid reservoir. There is a valve, then pump. After pump, the dead weight piston gauge assembly is connected. And another side, transducer under test or calibration we have to connect. So first, by opening the valve, hydraulic fluid, we will charge the pump, then we will close the hydraulic fluid reservoir valve, then we apply the pressure with the help of the pump. The same pressure will be exerted on the baits and the transducer element. In the balance condition, we can measure the pressure. We can calculate the pressure of deadweight tester by the formula mg over A, and the same time what is the reading of that transducer, we can calibrate it. So for calibration, we need a deadweight tester or any high primary standard or any high accuracy instrument to measure to calibrate the instrument. And this is done, all the standards in India kept in National Physical Laboratory. I worked there for 5 years also on different standards. So all the standards, they are kept in the National Physical Laboratory, and everyone has to calibrate their instrument in the National Physical Laboratory. All the parameters are there to calibrate. For low pressure, we use air, and for high pressure more than 500 psi, we use the oil. The capsule pressure sensor can be developed using ferroelectric material also. In ferroelectric material, they exhibit high electrostatic, means when we apply the pressure on these ferroelectric material, their capacitance got changed, and that can be used to measure the pressure. So one typical type of ferroelectric material is PVB1B2O3, lead-based ferroelectric material. This is widely used to measure the high electric capacitor, high dielectric constant capacitor in actuators and many other devices. Now it is used to energy storage also. I used this material to measure the pressure. What is the property of this group? This possessing high dielectric permittivity, a broad diffuse phase transition over a temperature range, and a strong frequency dependence. So this broad diffuse phase from paraelectric to ferroelectric phase, we can use. This is diffuse, means like in my case, in 10 to 50, 10 degrees centigrade to 50 degrees centigrade, the change of dielectric permittivity was almost constant. So it is not changing with the temperature, but it is changing with the pressure. So we can utilize, we can use this property to measure the pressure, accurate pressure, and which that pressure is not changing with the temperature. In lead-based ferroelectric material, the PFW is more useful for many devices because it can sintered, it can calcine at low temperature. So in PFW, the lead iron tungstate, PV site in octahedral site, B site is occupied by iron and tungsten, and A site is occupied by lead. So this lead iron tungstate relaxer material can be used to measure the pressure, and in upcoming slides, I will discuss how I optimize the processing parameter to make lead iron tungstate as a pressure sensor. So first time I use this lead iron tungstate material to measure the pressure, other than the many other application already was in used. So how I constructed this sample of PFW, I took the lead iron tungstate, lead oxide, tungsten oxide, and the iron oxide very high purity, in high purity, murk and eldritch. Then these oxides are mixed by grinding and then calcined at different temperature. So by weighing the accurately, then grinding, then calcined, after that it pressed into the pellets of 18 millimeter in diameter and 1 to 2 millimeter thickness using the press. So up starting from the oxide, I got the pellet in the form of this cylinder. Then this pellet was sintered at high temperature 1143 Kelvin to 1523 Kelvin for period of 1 and 2 hours. Then silver electrode were deposited on these pellets. So what will happen inside the circular plate, the both end having the silver plating. These silver is acting as a plates of capstar and lead iron tungsten acting as a dielectric medium between two plates. So dielectric constant of this was nearly 1500. So it increased the capacitance of this capstar by 1500 times. So we can have the sensitive pressure sensor. Then the capacitance of measured with the help of the brace, it can measure the at 1 kilohertz I measure this capacitance of this pellet and it can measure the capacitance very and loss factor at very high accuracy. So capacitance was measured in picofarad and the dielectric loss was measured 10 delta all the specimen as a function of temperature and pressure. For measuring the capacitance is the function of temperature, we kept this specimen sample in the pressure cell in a cell. I discussed the structure of the cell in later slides and then connected to the capacitance measuring device and that kept in the bath, constant temperature bath, accurate of 0.1 Kelvin. Then temperature set to the any particular temperature of interest, then capacitance is measured. So first I measure the change of capacitance in term of temperature. Then I measure the change of capacitance of this sample with the change of pressure. So this structure, this is a flow chart of, this is the figure for measuring the capacitance by changing the temperature. So this is pressure cell. Pressure cell was especially designed because I have to work on very high pressure up to 500 megapascal. So this is especially designed cell. Here inside in the center, we have to keep the center flange. There are the two other flanges in the two sides. So two sample it can accommodate. And after putting the sample in the golden value, then we have to close this cell and it form in the form of cylinder and then it kept to the pressure cell. So to measuring the capacitance, how we can do, here is the pressure generating device. With the help of the air compressor, oil tank, operated pump, intensifier, we are generating a very high pressure up to 500 megapascal. Then in this pressure, generated pressure, high pressure sent to the parallel for pressure measuring device and at the same time with the pressure cell containing the specimen. So we can read the pressure with the help of the pressure measuring device, accurate, and the capacitance of this specimen after applying the pressure. So this will give the relation between capacitance and the pressure. Change of pressure will generate the change in capacitance. So this is the graph of change of dielectric, relative dielectric constant with the help of the temperature and pressure. Pure PFW, lead, iron, tungstate material. Constructed at different temperature, 4 temperature, 1023, 1063, 1083 and 1103 Kelvin. So I use these 4 sample, change the temperature and measure the dielectric constant. And graph is plotted. Left side it is temperature versus relative dielectric constant. And in the right side, the same sample used to measure the pressure change of dielectric constant with the help of the pressure. So I went up to 415 megapascal. So these are the measurement result for PFW specimen prepared at a different calcination temperature. So calcination temperature 1023, dielectric constant was 1438. Then if I increasing the temperature, calcination temperature, the dielectric constant is increasing. Same material, but by changing the calcination temperature, the dielectric constant got changed. Same time, the loss also increasing, but the pressure coefficient was decreasing. And the temperature coefficient also decreasing, and for 1103 Kelvin, it becomes positive. So we need high pressure coefficient and less temperature coefficient. So we have to optimize the parameter for these specimens. By increasing the calcination temperature, what is happening? Because the chance of lead is evaporate. So it came my mind that if I increase the lead content, excess lead, if I put the excess lead, then maybe I can optimize the pressure coefficient. So I added 5% excess lead in the PFW specimen. Then result was that. So these are the result of the calcination at the same temperature, but additional 5% lead oxide is added in the sample. In next table, I will show the and same measurement I did here on all 4 samples. Temperature versus dielectric constant and the pressure versus relative dielectric constant. And then I noticed this change. The increment is not too much in dielectric constant. Here at 1103, the pressure coefficient was -133. Here it becomes -392. So it increased. So maybe in the structure there got change by adding the 5% excess lead oxide. And pressure coefficient is also not too much. It is very less, 0.002. Temperature coefficient is less. So trend is the same. The dielectric constant increased with the increase in calcination temperature. Loss increased, but pressure coefficient decreased, but not to extent. It decreased a less, and temperature coefficient also decreased. Then it came in my mind that why should not I react with this iron and tungsten first, then after adding the lead oxide. So this method is known as two-step calcination process method or Columbite process. In this process, the B side oxides are mixed for calcined first, then A side is calcined at lower temperature. So then I use the Columbite precursor method to optimize the processing parameter, and this is the result for Columbite method. I used here or prepared only 3 samples here at 1023, 1083, 113. Two-step calcination process. And the result was the change extremely high Dielectric constant increased 2773 for this temperature, lower temperature, and again decreased, then increased 6460. So dielectric constant increase a very large extent, and also the pressure coefficient is increased using this method. Minus 633 into 10 to the power minus 12 for 1103 Kelvin. And temperature coefficient is also less. So conclusion was, on increasing the calcination temperature of a specimen and adding 5% PFW, the dielectric constant and loss increased. Pressure coefficient of dielectric constant decreased. Temperature coefficient of dielectric constant become positive. Somebody asking Devani PFW. PFW is, in earlier slide I explained, lead iron tungstate. This is a relaxer material. On increasing the second calcination temperature, the specimen of PFW prepared by Columbite route, the dielectric constant is 6460 and loss is 0.4 at highest. Dielectric loss increase and highest among all method, and temperature coefficient of dielectric constant become positive. So Columbite precursor method is more appropriate the pressure sensing specimen, and it is possible to develop the pressure sensor to measure high pressure up to 450 megapascal using relaxer material. Still work is required to linearize the variation of dielectric constant of pressure and lower down the variation of dielectric constant with temperature. So this change is not linear actually, this is quadratic change. So if we can optimize, if we can make the change linear, then it will be directly can be used to measure the accurate pressure sensor of high pressure in high pressure range. So this is all about for my research. These are the references I took from. Dr. Ashutosh, maybe I finished before the time.
Thank you very much, sir. No problem, sir. No problem. Actually, it was very interesting and enlightening topic, which we wanted to understand how this pressure actually plays a very important role, because most of the weighing and measuring instruments are based upon load cells, strain gauge type load cells, or the shear beam type load cells. They are basically load cells, and how the pressure converts into the capacitance, resistance, or frequency. It is very important. With the help of that conversion, we actually get the actual weight of the load cell or the weighing machine. So it was certainly very eye-opening. I would like to request all the participants if they want to ask something, number one. Secondly, sir, now as you are here, I would like to take this opportunity to take this presentation to share with all our participants, with placing this video of today's in our local portals or in our legal metrology portals, so that the part whenever anybody wants to take an advantage of it, he can take. It was a very good exercise, very good article. Thank you very much, sir. Sir, Mr. B.N. Dixit would like to ask anything, or anybody else would like to say something?
So it was very nice lecture, and credit goes to Dr. Vinay Kumar and your team who is organizing such programs. I hope that in future this type of program will be successful.
Thank you very much, sir. Thank you for your kind words. Anybody else who would like to speak or would like to add anything else? Sir, actually, we wanted to have more knowledge on these, sphygmomanometers things, because in legal metrology, as you have already shown this pressure gauge tester. It is also very important. At the same time, this manometer testing or the spike move manometer testing is also very important. We have the testing facilities available at our reference laboratories or other laboratories in India. But how to do this testing, how it impacts the parameters, what are the things which impact this, would like to discuss with you. Not this time, maybe next time. Anybody else? I would like to request all the participants to kindly switch on their video and switch off their mics so that we can take your pictures, your photographs, and placing on our legal metrology portals, Twitter, Instagram, Facebook, and LinkedIn. So all these photographs will be available on this with the video, and we can take advantage of this knowledge sharing at any point of time. Anybody else who would like to speak, please? If you want to ask anything, you are free to open. Professor Vinay Kumar, basically he is an Indian, but working in Dubai. So we thought that we must take the advantage of his knowledge and experience for sharing our own people who are working in the field of legal metrology industry and all. Santoshi, you can take pictures, please. I would like to thank my NIC team. Professor Dwivedi is there. Dwivedi sir, what I was requesting you, Professor Kumar and Professor Dwivedi from ILM, I wanted to have one, one series of one by one equipment of the weighing and measuring instruments, so that, in a month, we will be having one lecture, let's say, starting with non-automatic weighing instrument, completely just covering the OML recommendation, the complete OML recommendations, the testing. Kindly switch on your mics, please. Switch on your mics, please.
Agarwal sir.
Yes, sir.
One thing I want to have question.
Please.
Regarding deadweight tester.
Sir.
The deadweight tester, whatever the weights they are using to make the reference pressure, so is it required to be calibrated by our traceability?
Sir, whenever you are using a weight, obviously it should be traceable. Actually, many times they are using the kilogram weights, or they are using the Newton weights. But they should be traceable, and the value should be correct. It is very much required. Otherwise, the testing which you are doing or the use which we are actually finalizing may not be correct.
That's what I'm telling. That tester, because
Yes.
different size of weights are being used in deadweight tester.
Yes, there are many times they are Newton weights.
Pressure is being calculated based on their weights.
Yes, sir. Yes, sir. So
So
they must be calibrated.
That because although it is treated as primary, but still I think that mass has to be cross-checked by our traceability. Then only proper pressure can be given in the deadweight test. I think so. Second question is
mass and area also, sir. Mass and area of the piston.
area will be the fixed, that there won't be any change in the chamber. But as far as weights of different pressure you are operating, so definitely that mass, if it is changing due to repetitive use or maybe the any reasons, that must be cross-checked time to time. That is one point. Second point is regarding pressure suit in the higher altitudes used by our jet pilots. Although the cabin is used CPCV, that control valve units for maintaining the pressure. So this pressure suit, again, they are using any further purpose is there for them?
Sir, actually, whenever we are taking the weight, even you will be surprised to know when this ISRO and all, they are getting their weights calibrated from RRSLs, regional reference standards laboratories. So basically the purpose is what weight you are actually taking on, what is the actual weight at the ground, at the head side. If you will consider the G, it is not very different because the height is not up to that level which will actually affect or make the difference in considerable difference. But certainly there will be a difference, obviously.
Thank you very much.
Sir, so what I would request you, Dr. Dixit, Professor Dixit, Professor Dwivedi, what I was thinking, if we take one by one equipment and just explain, make a series of, let's say, non-automatic weighing instrument, considering the complete OML structure, what are the requirements OML, how to test this as per OML, so that and how to develop, how to make an equipment or develop an equipment on the basis of these OML recommendations. It will be very good. So my request will be, if ILM can start, at least in a month, we will be having one lecture on one topic, let's say non-automatic weighing instrument, maybe 2 hours, maybe 3 hours, or maybe 4 hours, if required. Not in a day, it can be it may be continued for 2 consecutive weeks or 3 consecutive weeks, so that at least one article will be very clear about the non-automatic weighing instrument. Then we may have 117, the flow meters and the dispensing units. So these things can be considered, and we will be having the regular articles, regular lectures on this. We will start with this. I think ILM Rachi can support us on these topics individually. So with this, I would like to thank all. We will be having next week with the next topic, next Saturday. Till then, thank you very much. Thank you, NIC team, for supporting us.